And what they've been observing are collisions of black holes. So you can imagine how extreme colliding black holes. It's an incredibly extreme event. So it shakes the fabric of the universe, and the ripples come across the universe. And these laser beams, just based on lasers, can detect it. They just ring almost, just vibrate as the ripples go through. In space and time. Kip Thorne got the Nobel Prize last year for this. He's one of the greatest living physicists. So I once saw him describe it as a storm in time. So you've got a time storm. It's a beautiful image. So that technology is incredible because the change in length is, I can't remember the exact number, but it's way, way, way less than the diameter of an atomic nucleus. So the change in length of the beams is tiny, but we can do it.
So this a collision of black holes, the idea that you can detect that.
Yeah.
That.
Yeah. The first paper they published, there are 2 black holes, and they were about 30 times the mass of the sun each. And they're orbiting each other and spiraling in towards each other. And they accelerated. At one point, they were approaching each other at 1/3 the speed of light. And they accelerated to 2/3 the speed of light in 10th of a second. And then hit each other. And the explosion, the energy release, was, I think I'm right, it was something like 50 times the energy release. The power of all the stars in the observable universe glowing. And it was something like 50 times the amount of energy for a tiny fraction of a second. But it's an unimaginably violent event. And that's why our detectors can see the ripples that makes in space and time. And we detected, I can't remember, it's 2 or 3 of them, and also 2 neutron stars colliding. We saw that as well with it. So it's an incredible machine, which is why it got the Nobel Prize.
Now here's a supermassive black hole at the center of every galaxy.
Yeah.
But there's also other black holes that aren't necessarily in the center of galaxies.
Yeah, so these little ones, they're a few times the mass of the sun, and they're from black stars. So they are stars at the end of their life, very bigger than the sun, more massive than the sun. But they run out of their fuel, and they start to collapse as gravity squashes them. And if they're sufficiently massive, then there's nothing that can stop the collapse. And so they collapse, as far as we know, to a point, essentially an infinitely dense point. We don't really know what happens we don't know what happens right in the middle. But they collapse to such an extent that there's a region around them.
Changing mag!
And that's so nothing can escape. And that's a black hole.
And what happens to them? Do they travel? Are they moving through space?
Yeah, they're still stars. So they're still there. They're surrounded, this region where if you fall in, it's called the event horizon. And if you go across that horizon, then you are going to the centre. There's one way of thinking about it, which is quite cool, which is that the time and space sort of flip is one way to think about it. So in the same way that we are going into the future now, so we're going to tomorrow. There's nothing we can do about it. We are going to tomorrow. In the same way, if you fall in across the event horizon of a black hole, you are going to the singularity, it's called. So that's your future. Every line of your future points to the centre. So it's kind of the ultimate of no escape, the ultimate prison. You're going to get squashed to an infinitely dense.
So not every star becomes a black hole at the end of its life?
No, because if something like the sun, then
a small star.
It's quite small, yeah. And when it collapses, there's a sort of a pressure force, if you like, which is caused by the fact that electrons don't like to be very close to each other. So it's called the Pauli exclusion. Essentially what happens is that, so as they get squashed closer and closer together, they move faster and faster to get out of each other's way, if you like. And that makes a force which holds them in. And so that creates a white dwarf star. So you can have a blob of matter. They're about the size of the Earth, but they're about the mass of the sun. And so that's for smaller stars. They end up as these white dwarf things. They're very dense objects. There's another version which is called a neutron star, which is the same thing but for neutrons, and they move faster and faster. So if it's massive enough that it overwhelms the electron thing, and the electrons sort of crush into protons and turn into neutrons, and the whole thing starts again. And so a neutron star can be, you know, at least 1.5 times the mass of the sun, let's say, but it can be about 10 miles across. So that's an incredibly dense ball of matter held up by this. The neutron's moving around. It's got a fancy name. It's called neutron degeneracy pressure, but that's what it is. But if you go even bigger, then even that can't hold it up. And as far as we know, then there's no known force that we know of that can hold the thing up. And so that's when it just almost winks out of existence, if you like. It collapses and collapses and collapses.
Perspective, the sun is 1,000,000 times bigger than the Earth.
Yeah.
And this neutron star is, we just said 1.5 times the mass of the sun,
Yeah, so
but 10 miles wide.
Yeah. So, and there's loads of those around. They're called pulsars. So we see those. The first one that we discovered was called LGM1 because they spin very fast. And it was called LGM1 because it's a very regular pulse, and they thought it was Little Green Men. So they called it kind of jokingly Little Green Men 1. And so yeah, we've seen there's one called the Crab. We saw the supernova explosion. So that's when one of these stars explodes at the end of its life and then collapses, forming neutrons. And we saw it.
Taking effective.
Wasn't there some speculation that our solar system at one point was a binary star system, and that one of those stars had become a dwarf?
I don't know.
Someone had read
that.
something about that in relationship to a dense object they believe is outside the Kuiper Belt.
Yeah, I mean, there's some evidence, there's a bit of evidence that there's something. Yeah. But because of the periodic extinctions on Earth, you get periodic bombardments from the So yeah, I think one of the theories is
Periodic extinctions.
well, yeah. So think about there have been mass extinctions on Earth when a lot of the life died. We don't know what caused all that, but sometimes they're impacts from space. That seems clear. And so yeah, there are theories that there's something orbiting out there which can disrupt the objects out there. It sends loads of comets and asteroids inwards to the inner solar system.
Our UAV is orbiting the area.
Tossing sticky grenade!
And so there's some people. I mean, I don't know. It's one of those. It is a possibility. That there's something.
The speculation was that there's something out there. Correct me if I'm wrong. Something called the galactic shell. Like when it gets to a certain distance, there's something far out there.
Yeah. I mean, I think. I don't know the exact about the stellar-sized or mass objects out there. I don't know that. I mean, there are some sort of suggestions there's another planet out there, a big planet. But you're right. There can be stuff orbiting way beyond the Kuiper Belt, and we're talking, a light year.
It's interesting because it's incomprehensible, the distance, right? In our minds, how far that must be out past what we used to call Pluto. But for whatever reason, that becomes more interesting because it's in our neighborhood. Whereas if they find this star system, they might have a planet that's similar to Earth, that doesn't seem as compelling for whatever weird reason.
No, yeah, I mean, I think the planets around Alpha Centauri, Proxima Centauri, which are the closest stars, it seems like there are planets around those now. And I think that was interesting because we could conceive of going there.
Right.
And there was this idea, Stephen Hawking actually and some others, before he died, had this idea called Breakthrough Starshot, which is the idea to send a little probe out to actually sense the Alpha Centauri system. I think in their view, Yuri Milner as well, the entrepreneur, wanted to do that. And it was something like 100 years travel time, something with our current technology. And they point out that we don't do that now. We don't think 100 years in the future. If you go back when people were building cathedrals, people used to routinely start that would take 100 years to bear fruit. And so we could imagine going there. And that then becomes fascinating, I think, because then you've got a solar system, another solar system that you could go and visit. Conceivably.
Conceivably. Yeah, I mean, what kind of speed are we talking and how long would it take to get there?
Well, yeah, I mean, so it is. I think that the idea was about 100 years to get there. So it's going 4 light years or so in 100 years, so whatever that
So
is.
you would have to essentially do
Ah, voilà. This is it.
Oh, you're a robot
Yeah.
probe. It wouldn't be a crewed probe.
wouldn't be possible for a crew.
Well, it is.
You have to freeze them.
Yeah, that's always, when you talk to engineers, you had Elon on, didn't you?
Yes.
Engineers always say, physicists go, well, it's possible in principle, so over to you. You do it now. There are no laws of physics that tell us we
Right.
can't do it, so we just do it.
Right.
But, it's...
That's a weird relationship
It's
between the
hard.
physicists and the engineers.
Yeah.
Yeah.
But yeah, in principle, you're right. If you can send a little robot spaceship there, you can send a crewed spaceship there.
I'm of the opinion as time goes on and augmented and virtual reality gets better and better, that it doesn't really totally make sense unless we're talking about colonizing someplace to send biological life to another planet. And if we can send some probe that doesn't have to worry about the biology being affected